Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. So today we will be talking about the final exam question, the past final exam question for chapter 3. Yeah. So we have two exam question that we will discuss today from chapter 3, which is force vibration systems. Yeah. For single degree of freedom system only. All right. So let's look at the questions straight away. Yeah. Without further ado, let's look at the questions straight away. Okay, so let's say we have a light machine tool of mass m, 80 kilograms. So we have a system here with mass of these systems, with the block mass of the machine is 80 kilogram, is mounted on an elastic foundation, okay, which is we have elastic foundation here, K and C, as it is schematically shown in figure question 3. So this is the schematic diagram of the system. An experiment is carried out to determine the stiffness, K, and damping property C of the foundation. When the tool is excited with a harmonic force of magnitude F is equal to 4,000 Newton. So given in this question, you have the magnitude, which is F naught in this case, of the force exerted to the system is 4,000 Newton. And increasing frequency, which is your frequency is not stationary frequency, it is a swept frequency from 0 to infinity. So if you still can imagine here our plot, yeah, for magnification factor, we have a range of frequency ratio, which is R, from 0 to infinity. And in this case, you are given with the information of increasing frequency omega from 0 to infinity. The maximum steady state amplitude given in this case, the maximum steady state amplitude X max is equal to 4 millimeter, is obtained at operating frequency of omega is equal to 40 pi radian per second. So this is given to you. All right. So let's solve this question together. All right. So determine number A. Question A, determine the relationship between the maximum steady state amplitude and frequency ratio. So this is similar with your test question, yeah. So determine the maximum relationship between the maximum steady state amplitude and frequency ratio. So let's solve question A together. Okay, so let's solve question A together. So we have question A, yeah. So we know that the magnification factor for the force vibration system, we know that the magnification factor M is given by it's given by X divided by delta is equal to 1 divided by 1 minus R square plus 2 zeta R square to the power of 1 over 2, which is square root. All right. So in order for us to determine the maximum steady state amplitude, which is we want this one, we want this X maximum steady state amplitude. The maximum relationship in between steady state amplitude and frequency ratio. It's mean here that you try to get the magnification factor max when this one is occur. Okay, so it will occur at dm with respect to dr is equal to 0. So we know that if we differentiate the magnification factor with respect to the frequency ratio and then equate it to 0, you will get the maximum magnification factor, which you get the maximum peak, the maximum peak, something like this one. So we know that our plot is going to be something like that one. So this is going to be the location or the condition that we are interested to know. Okay, the maximum. So we want to know what is this R max and what is this M max, the maximum. So this case occur for damped case. For undamped case, it will go to infinity at resonance. Okay. All right. So now let's solve this one together. So we have, if we differentiate M, if we differentiate the M with respect to R, and then we know that our equation here, it is basically this equation, our equation here, this equation, yeah, it is basically 1 divided by 1 terms. So if you recall back, yeah, from the mathematical derivation or integration that you learned before this, we can differentiate this function here, this term here, this expression here, using the division formula, yeah? And then we know that when we differentiate the numerator here, you get 0, and then any numbers multiplied by 0, you get 0. And if you maintain 1 and then you differentiate the below terms, you get whatever the answer. Okay, and when we equate this one is equal to 0, we know that straight away the numerator will be there, but whatever value down here you multiply by 0, you get 0 straight away. Okay, so we know that using this one, okay, so we know that okay, so if we differentiate that one, so let me do this one here. So dr 1 divided by 1 minus r square minus minus 2 zeta r plus square to the power 1 over 2. Means that, okay, if we bring all these terms, it's going to be something like this. It's going to be something like this. 1 minus r square plus 2 zeta r square to the power of 1 minus over 2. Okay, so when we differentiate this one, we know that 1 over 2 will go to the front, and then this is going to be to the power minus 1, you get minus 3 over 2. So it's going to be something like this. So minus 1 over 2 multiply whatever term inside, we differentiate the term inside this one, so you get 2 multiplied by 1 minus r square multiplied by minus 2r, okay, plus, okay, so we differentiate the inside term, so you get 2 multiplied by 2 zeta r multiplied by 2 zeta, okay, and then this one is going to be equal to, right, so this one is going to be equal to, let me check, there's something else over there, so admit, okay, so this one is going to be equal to 0, so this is to the power of and then we multiply by the whole terms to the power of 2 plus 2 zeta r to the power of 2 to the power of 1 minus 3 over 2. That is equal to 0. So if you look at this one, we know that we can write this as minus 1 over 2, 2 multiplied by 1 minus r square multiplied by minus 2r plus 2 or 8. Let me leave this one as it is, 2 zeta, and then we divide it back by 1 minus r square plus 2 zeta r square to the power of 3 over 2. That is equal to 0. Okay, so we bring this one to the as a denominator back, and then we get this one. And we know that if we multiply this one to the other side, you get 0. Okay, and then if we bring this one to the other side, you get 0 as well. Okay, so what we left with this derivation is, so this is dm dr is equal to 0 is equal to, we will left with 2 multiplied by 1 minus r square multiplied by minus 2r plus 2 multiplied by, or let's get 8 so 8 zeta square r is equal to, put 0 in front of that, and then if we solve this one further, solve this one further, so we know that 8 zeta square r, okay, multiplied by this 2 multiplied by 2 multiplied by 2, you get 4r, so we get 4r, so this 2 multiplied by r square, so you get r to the power of 3, okay, so that is positive, so plus 4r to the power of 3, okay, 4r to the power of 3, and then minus 4r square, that is equal to 0. Okay, 4r square, that is not 4r square, that is 4r, sorry. Okay, so that is 4r, and then 2 multiplied by 2, so you get plus 4r squared. Okay, so when we arrange this one, you should get something like this. We divide it by r, so we divide this one by r, so you get something, and divide by 4, so you get 2 zeta square. Okay, divide by r plus 4, divide by 4 and divide by 4, then you get r square, and then you get minus 1 is equal to 0. And if we rearrange further this one, we know that we get 1 minus r square is equal to, or r square, we know that, we arrange this one, we get r square is equal to, bring 1 to the other side, you get 1 minus 2 zeta square. Alright, and then we know that we get r is equal to 1 minus 2 zeta square. So this is the value of r max. This is the value of this one. So you get the maximum r value, okay, for maximum magnification factor, right? And then if you substitute this r max into m for mx, okay, so we know that our m here is equal to 1 divided by bracket 1 minus, what is your r here? So your r here is 1 minus r squared, so you get 1 minus r squared, so 1 minus 2 zeta square to the power of 2, okay, plus, okay, so we get 2 zeta r, okay, so you get 2 zeta multiplied by r, which is 1 minus 2 zeta square, and then this whole thing is to the power of 2, and then this whole thing is to the power of 1 over 2. We substitute that into the magnification factor equation. Okay, and then if you solve this one, you will get mx. If you solve this one further, you will get mx is equal to 1 divided by 2 zeta multiplied by 1 minus zeta to the power of 1 over 2. Okay, so you should get this one. Alright, so this is the answer for question A. This is the answer for question A here. Okay, the relation between the steady state amplitude, which is x over delta, which we represent it as magnification factor, with the frequency ratio. So at r max, okay, at r max, you get m max. Alright, so that is the answer for question 1. Okay, guys, any question for the first one? Any question for the first one? Any question? Okay, all right, so that is the first one, yeah. Okay, so that is the first one. Now let's look at the second question. Okay, so determine the natural frequency omega n and the damping ratio zeta for the of the foundation. So in this question, you will you have asked with the what we call it as the natural frequency and the damping ratio, and we know that we derived this one many times. So this is for question B. Yeah? This is for question B. For these systems, we will have our equation of motion in terms of mx double dot. We derive this one. We have derived this one plus cx dot. Since we use the x as coordinate system, plus kx is equal to f sine omega t. Given in this question, f sine omega t, like this one. Okay, and then we know that using our formula, so omega n is equal to k equivalent divided by m equivalent. All right. Okay, that is the equation. But in this case, we don't know what is the k value here. It is not given. We don't know what is the c value here. It is not given, and we just have the mass value m, which is 80 kilogram. All right, so we should use different type of equation in order for us to solve this one. Okay, so we know that the omega divided by omega n, okay, is equal to in this case is equal to R max. We derived it before. Okay, which is in this case is equal to search 1 minus 2 zeta square. Alright, and if we rearrange this one, so let's define all the maximum value. So what is the R max in this case? So we have, it is given here in this question, the maximum amplitude is 4 millimeter at the omega of 40 pi here. So we know that our X max is equal to 4 millimeter, which is, I should write it as 4 times 10 to the power of minus 3 meter. And we know that our omega in this case is equal to 40 pi radian per second. Okay, so that is our frequency. It is 40 radian per second. So if we use this expression here, we should get the equation of omega n. Okay, so we know that the omega n square is equal to, so we use this equation, to express the omega n in terms of omega and 1 minus 2 zeta square. So we get the expression of omega square divided by 1 minus 2 zeta square to the power of 2. Okay, so why to the power of 2? Because we square this terms here, and if you square this terms, you will get this one. So if we rearrange this one, we get the omega n square is equal to, what is omega in this case? You get 40 pi square divided by, since this is square root and you get square there, it will be cancelled out. So you have 1 minus 2 zeta square. Okay, that is your equation number. So let's put it as equation number 1. So that is our first expression. And we also know that, let me divide this part here. So let's divide this part here. And we also know that the max, sorry, I use a black color here. So M max is basically equal to X over delta. Okay, so that is equal to, what is delta in this case? So delta, we derive this one also. So we get F divided by K, if you still remember. So if we rearrange this one, you will get X multiplied by K divided by F. And then what is K in this one? So K, if you use the equation here, if you use this equation, this one, if you use this one, K is equal to omega n square multiplied by M. So this one is equal to, let's use the red color, omega n square multiplied by M. And substitute everything here, so you should get M max is equal to, okay, so that is equal to X max multiplied by omega square M divided by F. And then we know that we derive this one. This is basically equal to this one. Oh, I forgot to put zeta square here. Okay, so this one, so you get 1 divided by 2 zeta, so multiply by 1 minus zeta square. Okay, that is M max expression. So let's use this one. So X max in this case given, which is 4 multiplied by 10 to the power of 3 meter. So we get 4 multiplied by 10 to the power of minus 3. That is the first expression for X max. And then omega n square, we use this one, So we use the equation 1 here. This is omega n square. So we use this one, and substitute it into our equation later on. Okay, so what is the equation? 40 pi square. So you get 40 pi square divided by 1 minus 2 zeta square. So this is a big expression, 1 minus 2 zeta square. Okay, and then we get multiplied by M, which is M in this case is 80 kilogram. Okay, M in this case is 80 kilogram here, given here in this question. Right, so multiply by 80, and then you divide it by F. So what is F in this question here? So F, we know that F is 4,000 Newton. So we divide it by F, which is 4,000. Okay, All right, and then this one is basically is equal to 1 divided by, so let's separate this part, two part here, 2 zeta multiplied by 1 minus zeta squared. All right, so now we have an equation with zeta expression here in this equation. So we can arrange this one further. So you solve this one simultaneously. So you should get zeta value is equal to okay. So you should get something like this. You can cancel this one. So 2.53. You should check the calculation. So these terms, this equation here, you can bring it down here. Okay, you can bring it down here, and then you solve the numerator part with the denominator part, and then solve for zeta. You should get zeta is equal to 0.128, or zeta, because this is quadratic equation, you should get 2 zeta is equal to 0.897. Okay. And then, since you have 2 zeta value, if you substitute zeta into this equation here, you substitute zeta back into equation 1, okay, and then sub zeta into equation 1, you should get 2 value. One is positive, one is negative. We will not use the negative value of zeta, the negative value of omega n. We just stick with the positive value of omega n. So in this case, we will use this one. So you will get the omega n in this case is equal to 127 point. Let me calculate it. 108. So if you 40 1 minus 2 multiplied by 0.08 to the power of 2. Okay, and then 40 multiplied to the power of 2. So you get 1.8 and the square root of the answer. 127.156. Okay, so you should get something like this. Something like this. 127.156 radian per second. That is your omega n. So okay, so the question number 2, determine the natural frequency and the damping ratio. So we determine the natural frequency and we determine the damping ratio. So we solve question 2. And question 3, see what is the stiffness value K of the foundation. So it is this one is very straightforward. So this is K. What is K? So since we have K is equal to omega n square multiplied by m, so we should get 127 square dot 80 kilo. Okay, so you should get the answer here. Let's me calculate this one. Okay, you should get the answer as 127.156 square 127.156 square multiplied by 80. So that is a 1294. It's something 1294. So you get 1294 times 10 to the power of 3 kilonewton. Kilonewton per meter. That is your answer for question C. And then for the last question, question D, suggest what can be done to reduce the vibration amplitude. So what you can improve, how you're going to improve the systems, or how you're going to improve the vibration amplitude by designing the systems. So what you can do for this one. So basically this is very straightforward. So if we look at our plot there, so we should start something like that, something like this one. So you got something like that, okay. So in order for us to improve, so this is M, this is R. So in order for us to improve the magnification factor here, okay, improve this one here. So what we can do? First, if you still remember, this one in the increasing value of zeta. Okay, if you increase the zeta value, so you increase the damping value, so or you increase the damping, okay, you increase damping, okay, so M will be decreased. It's very straightforward for this one, okay. Or for infinite at this region, at this region, let's use the blue color at this region for infinite value of R, so increase R, you will decrease M, okay. And in order for us to decrease R, so what is R here? What is R here? So R is equal to omega divided by omega N. And normally you cannot control the omega because it is from the manufacturer. The rotating part, the excitation part is basically come with the machine. You cannot control that one. But you can control omega N. Okay, so in order for you to increase the value of R, right, so you can decrease omega N. Okay, so to decrease the omega N, if you recall that this part is the mass region, so we can increase the mass. So if you increase the mass, you will decrease the magnification factor. So this is M. This M is magnification factor, yeah, not mass, yeah. All right, so you increase the mass. And another way to do it, okay, is basically we look at this region here. We look at this region, which is the stiffness region, close to static deflection, close to 1. Okay, so it is basically we want to get the value of lower value of R, which is we want to make it close to 1. Okay, so in order for us to close this one to 1, we can increase the K here. So this one, this region, we increase K. Okay, you increase the K value, then you will make the response or magnification factor moving toward the static deflection. Okay, so this is another region, but sometimes we be careful. We can control this one as well. We can control this one as well. We can control K at this region. So if you, so omega N is equal to set K over M. Okay, so in order for us to decrease the K, okay, to decrease the omega N, we can increase the K value for this one. But be careful, when you increase the K value here, it is basically you also increase the K over here. Okay, so it's similar. So either you increase the mass, which is you get lower magnification factor, or you increase the K value, you get close to static deflection, which is the magnification factor is close to 1. For example, like the earlier case, you have the magnification factor at this region, but when you increase the K, it will move to this region. Okay, all right, and then using this equation, if you increase the K value, you get bigger magnification factor. But you get bigger magnification factor, your R is going to be lower. So be careful. When your R is going to be lower, it's basically M is going to be higher. So this part, this region, okay, this region, sorry, I used the green color. Oops, sorry. Okay, this region, normally we are not controlling the K. Okay, we are not controlling the K, but we control the M for this region. So be careful. So if you want to use the reason for K, show it clearly. By increasing the K over here, okay, you get static deflection, which is you reduce the M if the earlier case at the region over here, okay. Or you can control K here, but be careful, you increase the K value over here, okay, you will increase the R value as well. So, sorry, you will reduce the R value. So when you reduce the R value, it might affect the magnification factor. So be careful if you want to do or to give the suggestion. Of course, mathematically, we can play around with this equation to get lower omega N, but in vibration, in reality, physically, you cannot control K at this region. You just control K if your system response fall at this region. But if your system response fall at this region, you can control M. And if your system response falls at the resonant region, you can control C. So hopefully this one is clear for you guys, yeah? So I think that's all for this example or for this exam question, right? So if you have any question, just ask me any question here. Any question, guys? Ada question? Okay. No question, eh? Okay, so sekali lagi saya minta tolong tulis nama dekat chat tu sekali lagi. Tulis nama penuh dekat chat. Tulis nama penuh. Oh, ada yang tanya. Sekejap saya tengok chat Okay, so dekat equation Mx tu kan sebenarnya omega kan dari bukan omega n. Kan sebenarnya omega kan dari doktor bukan omega n. So dekat Mx ya. So at this, oh sorry. Okay. Which one omega? This one This one Oh, this one is omega n. This one is omega n because this one is not from the magnification factor equation. This one is from K equation. So we substitute K into this equation straight away. So from K, it is basically omega. Omega n. It is not omega. Okay, it is basically omega n. Hopefully that answer your question, yeah. Okay, alhamdulillah. Alright. Okay, so please write your full names dekat chat session dekat chat room ni. Okay. So if you have no question here, let's discuss the second example. The second example. Let's discuss this one. Okay, so this is question, Alright. Okay, so the second example for the final exam question. So let's discuss this one. So we have a common example of base motion is the single degree of freedom system. So again, for chapter 3, we are still dealing with the single degree of freedom system. So an automobile driving over a rough road surface as shown in figure question 2. Okay, so this is the schematic diagram of the automobile. Okay, the road is modeled as providing a base motion. So this is as what I upload the video this week about the base motion. And the base excitation given by yt is equal to magnitude, and the amplitude is 0.01 meter unit. The unit is meter. Sine 10t. 10 is basically the omega. The suspension of the automobile provide an equivalent stiffness k, given the k here is equal to 4 times 10 to the power of 5, and a damping coefficient of c is equal to 30 times 10 to the power of 3. Okay, and the mass of the automobile is basically 1,000 kilogram. All right. So question A here, oops, let's use the black color first. Okay, question A, write down two assumptions used for this model and draw the free body diagram of the system showing clearly all the active force. So what are the two assumptions that you can use for these systems? Number one, you can use this is a linear system. That is number one. I always mentioned this one in the class before this. This is a linear system. You deal with a linear system. You are not dealing with the non-linear system. Or we make an assumption that our system is a linear system. That is number one. Number two, we can neglect the air drag, for example, or the friction from the air, or we can call it the friction from air. Okay, so we can neglect that one. All right, so meaning that the system will attenuate, the amplitude of the system will attenuate due to the suspension, due to the K and due to the C, not due to the friction from the air. Or we can make assumption that our road here is purely sinusoidal. Okay, the rough road here is purely sinusoidal, so because that we use our equation as sinusoidal equation. Okay, so we can make assumption that the road excitation is purely sinusoidal. Okay, all right. Okay, so that is the answer for question A. So you just need to answer with two assumptions only. Okay, so question B, derive. Oh, sorry. For question A, you still have the free body diagram. So this one, I derived this one in the e-note and also in the class. So Let's draw it properly. So we have this one, we have this one, we have this one, we have this one. And then we know that our input excitation y given the output, and we have the response output. So when we have the response output, we can make our assumption here, either it is in compression or it is in tension. So let's say it is in tension. So we can draw our FPD in compression here. Okay, we can draw our FPD in compression there. So this is from the root. So we know that this is K multiplied by, so since we make assumption that it is in tension, so x greater than y, so x minus y. And then this is C multiplied by x dot minus y dot. So this is the M, so this is the x. And again, we are not interested to know this one here. We are not interested to know this one here. So we will left with that one. Okay, so that is your free body diagram, the active forces that impose to the systems. Okay, we have two active forces. So that is answer for A. So let's answer for B. Okay, derive the equation of motion of the system. I derived it in the e-note clearly, and then I derived it in the other video clearly. So hopefully you can refer to my e-notes and my video. And finally, if we derive this one clearly using the Newton's law, we know that our equation summation of forces is equal to MA. Sorry, output is positive, so we know that minus K multiplied by X minus Y minus C X dot, C X dot minus Y dot is equal to MX double dot. And if we rearrange this one, you will get MX double dot plus CX dot plus KX. Plus KX is equal to KY plus CY dot. Okay, and by substituting this Y and this Y with Y sine omega t, and then this one is Y dot Y omega cosine omega t into the expression, we can rearrange it and represent it differently. And question B just asks you to derive the equation of motion. So this is basically the equation of motion for question B. So it answers your question straight away. But if you want to know the detail of this one, look at my e-notes and look at the other video that I uploaded to you, especially for base motion. You'll get the detailed derivation. Okay. So question C, based on the value given, determine the natural frequency and damping ratio. So for question C is very straightforward. So let me use the black color. So omega n and damping ratio zeta. So we know that from equation of motion, omega n is equal to K equivalent divided by n equivalent. And then if we substitute the K equivalent in this case here, given K equivalent is equal to 4 times 10 to the power of 5, and M equivalent is equal to 1000. So we just substitute it into the equation. This is very straightforward. So you get 4 multiplied by 10 to the power of 5 divided by 1000. Okay, you should get the answer straight away here. Okay, so what is the answer? Let me calculate this one for you. So we get 4 times 10 to the power of 5 divided by 1000. So square root of the answer. The answer is going to be equal to 20 radian per second. And then what is the zeta value? So this is very straightforward as well. So for zeta value, we still remember zeta is equal to C equivalent divided by 2 M equivalent omega n, or we can use C equivalent divided by 2 Z K equivalent dot M equivalent, or we can use another expression which is C equivalent divided by CCR. Either one, whatever information given to you, you can use either equation. So in this case, we have the omega n, we calculated it before, so we get zeta is equal to C equivalent, in this case given, which is the value is 30 times 10 to the power of 3, so we get 30 times 10 to the power of 3 divided by 2 multiplied by M equivalent, in this case is 1000, and then omega n is 20 in this case. So if we calculate this one, you should get the value of 30 to the power of 3 divided by 2 divided by 1000 So you get 0.75. Okay, 0.75. So this is underdamped system. So clearly, why underdamped? Because zeta is in between 0 and 1. Okay, so that is question C. And question D, determine the amplitude of the absolute displacement of the automobile. So means that for question D, you need to determine what is the X, the amplitude of automobile, not the road amplitude. It is given. So if we recall back, we can use the displacement transmissibility. So we know that TD is equal to X divided by Y. So what is the equation here? We have a big matrix here, so a big function here. We have 1 plus 2 zeta r square divided by 1 minus r square plus 2 zeta r square. That is to the power of 1 over 2. Okay, so in order for us to get the zeta value, to get the x value, so it's basically you just need to bring the y on the other side, on the left right hand side, and then multiply by everything here. So we get the zeta 0.75, we get the r. So we need to determine the r value. So in this case, r is equal to omega divided by omega n. Okay, so what is omega in this case? What is omega in this case? So it is given, it is given omega is equal to, see here, see this part here, 10, So omega is equal to 10, omega n in this case is equal to 20. So you get r is equal to 10 divided by 20, which is equal to 0.5. So by substituting everything here, all the values, we got 1 plus, so 2 multiplied by zeta in this case 0.75, and then r in this case 0.5 to the power of 2 divided by 1 minus, so r is 0.5 to the power of 2 plus 2 multiplied by 0.75 multiplied by 0.5. Okay, so this is to the power of 2, and then everything to the power of 1 over 2. And then we know that what is y amplitude. So y amplitude is given here, 0.01, that is y amplitude. So just substituting the y amplitude later on. Okay, so here is equal to 0.01. You should get your x is equal to, let's calculate this one, let's calculate this one all together. So you should get the x is equal to, okay, all right, 0.5 square plus 2 multiplied by 0.75, 0.5 square. So I forgot to put square here. Okay, that is a square, the whole things. And 1 to 1. That's square root, that's 1. So you multiply by 0.01. So you should get the answer here at 0.0118. Something like something around this value. If you get around this value, you should be the answer should be correct. Okay, so that is the amplitude. That is the question D. That is the amplitude, the absolute displacement amplitude of the car. So if you look at this one, by given that the amplitude of this one is 0.01, your car will displace with 0.0118 value. So is it good? It's not good. Why? Because you amplify. Okay, by given the amplitude of the excitation is 0.01, you amplify the motion of the person inside the car. That's not good. Okay, all right. So the question D, question D, this is question D, this is question E. So question E asks you, okay, suggest way to reduce the vibration amplitude experienced by the automobile passenger. So you need to suggest a way to reduce this one. Okay, so how to reduce this one? So to reduce this one, you need to look at the amplitude. So you need to look at this one. Okay, so at this region, okay, sorry, I think I have to open this one. So you need to look at the displacement transmissibility. You need to look at this plot. Okay, we need to look at this plot. So in order for us to reduce the amplitude x, it is basically we need to reduce the displacement transmissibility. We need to reduce this value. Okay, So how are we going to reduce this one? Yeah. So basically by increasing R, if you can see from this plot, if we increase the R value, the TD will be decreased straight away. From this region, it will decrease to this region. Okay, so that is one, right? So how to reduce the, or how to increase the R value? So R is equal to omega divided by omega n. So R, so for this one R, so increasing R, so you increase R, okay? How? So how? So TD is decreased if you increase the R. But how? So R is equal to omega divided by omega n. Okay, so in order for us to increase the R, so omega n must be lower, as I mentioned before this. So how to, so omega n is equal to K over m. So how to make omega n lower? So either we increase the m, okay, or we reduce the stiffness. Okay, but be careful again. If you reduce the stiffness here, you increase. If your initial case, if your problem falls at this region, if you increase or if you reduce the K, you will increase the TD. If your system falls at this region, but if your system falls at this region, you reduce the, so you reduce the K, you reduce the omega, and straight away. Okay, so for the K, be careful. But if you increase the M value straight away, you will increase the omega N. So you will reduce the omega N, and you also increase the R, and you reduce the TD. Okay, so this is one way to do it. All right. So another way. So this is the base motion. Yeah? This is the base motion. Another way. This is a base motion. So when we talk about the base motion, we talk about the omega. So R is equal to omega divided by omega n. So this one settle. Okay, this one settle. But this one, it depends on the traveling speed. Okay, it depends on the traveling speed because we are talking about a car moving on a rough road. So it really depends on the traveling speed. Okay, so if let's say we took the response, we took this one, so we took this one as one representation. So that is equal to y sine omega t. So if we took that one, if we took this one, so let's use as a sine function. Okay, so this is basically the amplitude of y. So this representation yt is equal to y sine omega t. Okay, y sine omega t. All right, so this distance for a car to travel from this one to this one, you have the speed there, velocity. Okay, and then this distance you have the, and also displacement, or we call it as distance. Okay, so we know that velocity, the unit is basically meter per second, and we know that the distance is basically meter. And we know that our frequency is basically 1/second. Just look at the unit first. And we know from here, you get the omega is equal to 2 pi f. Okay, which is in radian per second. So if let's say we rearrange our information here. So we have the omega over here to here. Sorry, use this one to this one. It really much depend on the 2 pi multiplied by f. So what is f here? What is f there? That is equal to 2 pi multiplied by, so f, the unit is 1/second. It is basically you have meter per second multiplied by 1/meter. So meter cancel out, you get 1/second. So you get f. So this is f. Okay, this is f. So meter per second is basically your velocity. Okay, and then you divide by the, we call it as the wavelength. What is the wavelength? Wavelength is this distance, the car travel. Okay, the car travel. All right. So in this question, it is not given, but sometimes you will have the wavelength. How far the car travel for the period under study, yeah? For the period of study. Okay, so if we solve this one further, you get 2 pi multiplied by v multiplied by 1/wavelength. Okay, for example, if let's say your car travel at 80 km per, this is an example, yeah, hour. So in meter per second, you get 80 multiplied by 1000 divided by 3600. Okay, so this is V, this is V. So you get the answer in meter per second. And this cuttable for 80 kilometer for 6 meter, for example. So wavelength is equal to, for example, as 6 meter. For example, means that you just take a certain period of time for 6 meter. So in order for us to calculate the omega here, so that is equal to 80 multiplied by 1000, multiplied by 1000 divided by 3600 multiplied by 1/6, and then don't forget to multiply by 2 pi. Then you get the omega. So in this case, in order for us to increase the value of R, we can increase the value of omega. Okay, in order for us to increase the value of R, we can increase the value of omega. So how to increase the value of omega? Another way, by increasing the speed here. If you increase the speed here, is basically, so if your speed is increased, your omega will also increase. There's another way to do it. Okay, so that's all for this question. Yeah. Okay, guys, any other question? That's all for today's examples. Yeah. Okay, no question. So I think if you have no more question, so we will stop our class now. So if you have any other question after this, you can post your question in the UFuture platform, or you can WhatsApp me straight away. Okay, so I will upload this video later on in the UFuture, and also the e-note for the rotating unbalance. And then please look at the UFuture every week, because I will upload new materials and also the e-notes. Yeah, I will upload the new materials. Yeah, for chapter 4 especially. So I think, guys, we will stop our class now. We will talk again later on Thursday. Okay, so thank you very much. See you again. Bye bye now.